Hello everybody and welcome back. I'm Jason and today I'd like to chat about a really cool and fascinating topic. My question to you is, have you ever wondered, is it possible for light to bounce off of light? In other words, for a photon to bounce off of another photon. For instance, if you shine two flashlights together, do the beams just pass right through or do they interact somehow? Today, I'd like to dive a little deeper into this really cool question, into the fascinating world of quantum mechanics to find the answer and talk in a little more detail about what light really is. Here in my hand is a laser pointer. I can shine it on my hand here, and hopefully you can see that. And here's a different laser. I can shine it, that's a red one. I can shine that on my hand there. Notice that the entire studio here is bathed in light. So photons are hitting me, hitting my hand, and this laser is also photons hitting my hand. Different colors, but the concept is the same. Now you can do this with any kind of light that you might have, a flashlight, a laser, sunlight, or any other source. What I'm trying to get you to see here is that I'm shining light and it's going through the air and hitting my hand, and the photons from the studio are also hitting my hand, but these beams of light that are in the same space are not causing any problems. They're not bouncing off of each other. In other words, it's something you take for granted, but photons can actually occupy the same point in space without kind of like messing around, for lack of a better word, with each other. In fact, I can take this laser pointer and I can shine it right into here and basically crisscross these two laser beams and nothing odd happens. We take this totally for granted. Now let's start with a surprising fact. In general, photons, which remember are the particles, quote unquote, that make up light, they actually pass right through each other without interacting at all. And this is because photons are actually in a class of particles that physicists called bosons. Now, bosons are particles that don't mind sharing the same space without any real interaction or fighting over the same space, for lack of a better word. In fact, they're perfectly happy to occupy identical, what we call quantum states in the same location. In fact, this is why laser beams can cross paths without affecting each other, and actually why multiple radio stations can broadcast through the same space without interfering. In everyday experience, we take this for granted, right? We know that our hands are made of something we call hard, right? Physical matter. Matter, like my hands, cannot occupy the same space at the same time with other matter. We say that if a particle of matter is here, you cannot take another particle of matter and put it right on top of the first one and occupy the same space. We might say they can get close together. We might say we can mash them close together, but we can't occupy literally the same location. But if you look around, I have lights from the studio hitting me, photons, trillions of them, streaming and hitting me in the face. But then I also have a little bit of sunlight coming from the sun, coming through the window and also hitting me. And then in the same room, I have radio waves. I have radio from my microphone going down and talking to the camera right there. I have photons coming from both of my TV screens that I have over there. That's all occupying the same space with the photons in the room. I have microwaves, which are leaking out of the microwave in the kitchen. A tiny bit of them leak out. They're coming over here and they're interfering. And there's infrared, there's all this other stuff. But the concept I'm trying to get you to understand is that we're seeing in this room, light is hitting me, it's bouncing off of me, and then it's bouncing off of the other walls. There are photons crisscrossing in front of you all the time. Not just the visible photons, but the infrared, the microwave, we can go on and on, ultraviolet, and they are not really bothered by each other. They're not causing a problem. They are not, there have no problem occupying the same space with the same quantum states, being the same type of particle called a photon. And this is precisely because when we talk about photons, we say they belong to a class of particle called bosons. Bosons in general can occupy the same space with the same quantum state. And don't worry if you're a little fuzzy with what is a quantum state or quantum numbers. I'm going to talk about that in just a second to clear it up. But wait a minute, if particles can share space, why can't I just walk through the walls? Why can't I just fall through the floor? Well, that's because matter, what we call the hard stuff that everything is made of very different particles, and those are called fermions. So fermions include the particles that you've heard of: electrons, protons, and of course quarks. Now quarks are the building blocks of the proton and the neutron, so that's kind of the fundamental deal. They're the fundamental building blocks of ordinary matter. So these particles follow something called the Pauli exclusion principle. You learn about this in chemistry and physics, and that basically says no sharing allowed. In other words, two fermions can never occupy the same location in space with the same exact quantum numbers. And that is the main reason why matter feels solid. You can't push into other matter because they obey this Pauli exclusion principle. And it also is the primary reason why everything in chemistry that you ever learned is true. We know that the electrons can occupy certain energy levels and orbitals around the atoms. And we say that the first electron goes to the lowest one, and then it can have two electrons in the lowest energy state. But then when you put that third one in, it can't be down there. That's because of the Pauli exclusion principle, because it can't have the same quantum numbers than the particles that are already there. So it has to occupy another energy state slightly higher up and at a farther radius away from the ones that are down there lower. And you fill up that shell, and when it's full, then the other ones that come in have to occupy a shell farther away. So hydrogen, having one proton and one electron, very simple atom, very, very small. But if you have something like iron or plutonium with lots of electrons, they are not all occupying that low orbital. They're stacked out, and so the outermost electrons are very far away from the nucleus. That is because electrons obey the Pauli exclusion principle and because they are fermions. So two broad classes in physics. Fermions cannot occupy the same space with the same quantum number. That leads to all of chemistry and matter. And then you have the bosons, which in general have no problem occupying the same space with the same quantum number. Mainly we're talking here about photons. Now, I've been throwing around words like quantum numbers and same quantum state, and I want to dive a little bit deeper so you know what I'm talking about. Now, they're a little mysterious at first, but they basically come from the solution to something you may have heard of called the Schrödinger equation in quantum mechanics. So here's a crash course in the basic idea of quantum mechanics. Every picture that you've ever seen in a book of how an atom is, it's not like that. And every picture you've seen in a book of how a light wave is, it's not like that. We don't actually know exactly what atoms look like when you get down to that level, exactly. And it could get into a lot of philosophy here. I don't want to get into that now. But we know that through experiments, everything that we see that has a wave-like nature, like a light wave, it also comes in discrete chunks, which behave more like particles. So we say that light has a wave-like character, and it also has a particle-like character because it comes in discrete chunks. Now, the same thing is also true of all the particles, the electrons, the protons, and everything else, the neutrons, all the other particles that exist in terms of matter. We think of them as particles. That's what you see drawn in books, but they actually have a wave-like character also. You ever heard of an electron microscope? Well, an electron microscope exploits the wave-like nature of electrons to see things that are really small. So we know all about this. This is a theoretical framework, but we know it's real, or at least there's some aspect to it that is real because we can build machines that use the wave nature of the electron. Right? All of your medical imaging also works in the same way. We have to understand the stuff to build those machines. So everything in the universe basically has some sort of wave-like character. So the equation called the Schrödinger equation is what governs how these wave-like structures, we call them wave functions, how they change over time. So the Schrödinger equation itself is a quite complicated differential equation. Actually, it's called a partial differential equation. It's a big fancy word in calculus, which just means it relates to the rate of change of things over time. Now, do you remember back to algebra when you were asked to solve an equation? Something, 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 something equals 0. And you were asked to find the answers to the equation. Sometimes you might get one answer if you had a line when it was equal to 0, when it crossed the x-axis. And sometimes you might get two answers if it was like a parabola and it kind of went up and down like that. Sometimes you might even get three answers if it does a wavy-like thing. You can get lots and lots of answers in algebra for regular algebraic equations. And those numbers that you get as the answer are special numbers that fall out of that equation. And when you have the Schrödinger equation, and when you solve the Schrödinger equation, you have these numbers that fall out of the solution. These are called the quantum numbers. And I'm going to describe what a lot of these quantum numbers are in detail in just a second, but let's just say when you use the Schrödinger equation to model what the hydrogen atom looks like, the simplest atom on the periodic table, then what you get is a solution with these constants that fall out. And the constants describe the different kinds of orbitals that these electrons can surround the nucleus of the hydrogen atom. It describes the shape, it describes the angular rotational state of the system, it describes the energy of the electron, and so on. And these numbers are called quantum numbers because all of the quantum numbers uniquely describe the different wave-like states that the electron can exist around the atom. You need to throw away the idea that an electron is a ball that goes around. It's not. It's a wave-like structure. And these quantum numbers really describe what that wave looks like. So just like in algebra, when you solve it, numbers come out of the solution. In differential equations, in the Schrödinger equation, the numbers that fall out of that solution are called the quantum numbers. So when I say two particles cannot have the same quantum numbers in the same location, I'm saying an electron here where my finger is going to have quantum numbers. And then another electron cannot exist in the same place with the exact same quantum numbers. Something has to be different, and it has to do with the type of particle it is that governs why they can't occupy the same space with the same numbers. The details of that go way beyond this lesson, and I'm not sure that anybody actually knows why fermions behave the way that they do. We're still searching for answers, don't forget, but we know that the quantum numbers one of them have to be different in order for the electron to be in that location, and for it to occupy the same space as another electron that's already there. So each of these fermions, so these are the matter particles, remember, such as an electron, but you could talk about something else, has a set of 4 quantum numbers that describe the state. You can kind of think of them like an atomic ID card, but what I said a minute ago is more appropriate. It describes the shape and the behavior of the wave description of the electron. So the first one is called the principal quantum number. That's really the most important one, really. It tells us how far the electron is from the nucleus. It describes the energy level or the potential energy that the electron really has. It's kind of like an analogy would be the floor of in an apartment building, what floor is that electron living on? Then you have another quantum number called the angular momentum quantum number. That one more describes the shape of the orbit, kind of like choosing between a circular or an oval shaped path. But in reality, electrons have much more beautiful shapes, and not just a circle or an oval. They can have these lobed structures that are quite beautiful in 3 dimensions. But that quantum number more governs the shape. Then you have what's called the magnetic quantum number, and that tells you how this orbit is oriented in space. So you can imagine tilting your orbit in different directions, for instance. Maybe it's oriented this way, maybe it's oriented this way or this way. It governs how the shape of the thing that the other number described, how it's oriented in space. And then finally, you have the spin of this spin quantum number. And so electrons, for instance, can either spin up or spin down, kind of like spinning tops. Now I want to caution you here because I'm blowing past a few things and I want to make sure you're clear on it. We say that electrons have spin, but they actually don't spin. There's a rigorous proof as to why electrons can't spin, but we do know that there's some angular momentum aspect to every electron. We can do experiments that really look at electrons in great detail, and we know that electrons produce a very, very tiny magnetic field. You know, when electrons flow through wires, they create a magnetic field. And when electrons are just sitting there doing nothing, they also have a very, very tiny, tiny magnetic field. It's called the magnetic moment of the electron. And depending on how the tiny, tiny magnetic field associated with that electron is oriented, either if it's up or down, we say it's spinning up or spinning down. Basically, that's the basic idea here. But because of the way quantum mechanics works, you can't have a spin sideways. I mean, you would think it can spin in any direction, but really electrons can be spin up or spin down. So when we learn in chemistry, you learn about spin, you learn about electrons filling into orbitals, and for an electron to have the same, occupy the same orbital, you have to have at least one of these quantum numbers different, and usually it's spin up versus spin down. Now I want to again emphasize that electrons for our current theories, are point-like particles with no dimensionality. So they don't spin like an actual globe, but they have angular momentum. They have some sort of angular character to them without actually spinning. And if that doesn't make sense to you, join the club. Nobody really understands quantum mechanics. The best we can do is provide analogies to explain what's going on. So getting back to the Pauli exclusion principle, it says that, again, at least one of those quantum numbers has to be different for the electrons to be on top of each other. It's like a cosmic rule that says no doubles allowed. And again, that's why electrons arrange themselves in different shells and subshells around the nucleus. They're not really being antisocial, it's just that they literally cannot share the same exact quantum state. Now, this fundamental rule shapes everything from the structure of atoms to the very nature of solid matter. And it's the fundamental reason why you cannot put two hands through each other. Now, this is where things get really interesting. Now, light doesn't behave that way. There's no Pauli exclusion principle for photons. Photons are perfectly happy occupying the same space, the same quantum state. It's happening right now with all the photons crossing paths going towards my face. So the answer to the question is photons cannot strictly bounce off of each other because they can occupy the same space and go right past each other. But under very special circumstances, light can actually appear to bounce off of other light. So a light wave can actually appear to bounce off another bit of light, or a photon could appear, I say the word appear, to bounce off of another photon. And this happens through a counterintuitive process, something called pair production. It so happens that in quantum mechanics, there are a lot of counterintuitive things. Now here's how this would work. When two very, very energetic photons get close to each other, they can briefly transform spontaneously into pairs of particles and antiparticles, so matter and antimatter, like an electron and its antimatter twin called the positron. Now, these particles can interact with each other because they're no longer photons anymore, they're fermions. So the matter particle and the antimatter particle that the photon transformed into, they're fermions, which can interact with the other fermion that are coming off of the other photon that has moved close by. Now, antimatter is fascinating all by itself. Remember, an antimatter particle has the same mass as the prime particle, but opposite charge. And there are other changes to some of these quantum numbers that I just talked to you about a second ago. But that's what a matter and an antimatter particle is. And if you remember back from Star Trek, if you have a matter particle and an antimatter particle, when they get close and interact with each other, they annihilate and they turn right back into a photon. So what we're trying to say here with the pair production is you can have a photon coming together next to another photon. They will not interact because they can pass right through each other. But through very rare circumstances, if this photon spontaneously changes into a electron and a positron, which is a particle and an antiparticle, and then this photon spontaneously changes to its pair, which is an electron and its antiparticle, the positron, then those two pairs of particles can interact and annihilate each other and produce photons again, and it would appear as if the original two photons bounced off each other, but in fact this complicated process happened whenever they got very, very close together. I'll say it one more time because it's kind of wacky and we need to wrap our brains around it. I want you to think of it like a subatomic dance. Two photons approach each other. They each transform into particle-antiparticle pairs. That's a real process called pair production. Then those pairs interact, and when they do that, they annihilate and they go right back into photons, so there's no more antiparticles or electrons anymore. And those photons are now traveling a new direction. So from our perspective, it can appear like the two light beams did, in fact, bounce off each other. But don't expect to see this happening with your household laser pointers or your flashlights or sunlight or anything like this, because this process is incredibly rare and it only occurs under extreme conditions. Now you have got to be asking yourself, how can this possibly happen? We were always told that, you can't just create something from nothing. How can this possibly happen? Well, quantum mechanics can get weird and we're going to get there. I want you to remember Einstein's famous equation, right? E equals mc squared. So to create even the lightest particles like electrons and positrons, which are incredibly low mass, you need photons with enormous energy, and we're talking gamma ray territory here. So each photon would need at least 511 1,000 electron volts of energy. It's just a unit of energy. And that's way more energetic than visible light. So this is not really going to happen with sunlight. It's not really going to happen with, your laser pointer or anything like this. You would need something much higher in terms of the energy of the incoming photons. So you have to also be asking yourself the following question. How can a massless photon, because photons don't have mass, right, suddenly turn into particles with mass? Doesn't this violate the law of the conservation of mass and the law of conservation of energy? That is a really good question. First of all, I want you to remember E equals mc squared. What it means is that every bit of matter, if I have my finger here has a certain mass, and if I put that mass into E equals mc squared, then, m and then c is the speed of light, and then you multiply again by c, the speed of light, because it's squared. The speed of light is huge, it's a big number. So mc squared is an enormous number for anything lying around on the tabletop. But even if you had like an electron, it would still be a very high energy. What that means is the mass that you have in any object laying around you has an equivalent amount of energy in the form of mass. You can almost think of it as ice and water. We know that ice and water is still H2O. Liquid water can flow, and ice, we sort of see it as a phase change or kind of a crystallization of the same stuff that the liquid water is really made of. And you can kind of think of that as a loose analogy of energy, and then you can have kind of a phase change, and then it's like the matter version of the energy that was there to begin with. So when I have this thing sitting in my hand, we say it has mass, but we also say it has an equivalent amount of energy. Same thing with photons. We might say that the photons, they don't have any mass, but they do contain energy. And if you don't believe me, just go out to the beach and stand under the sun with no sunblock, and you will see that those photons are putting energy into your skin, and they're making you have a sunburn. So photons have energy, and they would have an equivalent, according to E equals mc squared, an equivalent amount of mass. But because the speed of light is so big, in order to take the energy of a photon and convert it into any particle at all, you have to have a lot of energy in the photon to begin with. And that's why this pair production thing doesn't really happen with visible light. It has to have a very high energy photon in order to make something even as light as an electron and its antiparticle, the positron. But still, you might be saying, wait a minute, this goes against everything I learned in chemistry, right? You can't create something from nothing. Well, I'm trying to tell you that you don't have nothing to start with. You have a photon with energy, and that is equivalent to a certain amount of mass. And here is the clever trick that nature uses. When a high energy photon creates a particle-antiparticle pair, all of its energy of the photon gets converted into three things. The rest mass of the particle, one of the two of the pair. The rest mass of the antiparticle, one of the two particles of the pair. And any other leftover energy that the photon has becomes kinetic energy, making these two particles that you've now created physically move. And this is precisely why we need such energetic photons to do this thing anyway. It's because the energy has to be at least equal to the combined rest mass of both particles. So for electron-positron pairs, which are very low mass particles, that's about 1.022 million electron volts, 2 times the mass of an electron, since E equals mc squared. But there's another twist coming here, and it's from somebody you might have heard of named Heisenberg. According to the Heisenberg uncertainty principle, we all know that there's a relationship between the momentum and the position of any quantum particle. But actually, that can also be written in terms of energy and time. And energy conservation can actually be borrowed for extremely brief moments. So these particle-antiparticle pairs, they can pop into existence and disappear so quickly that they're called virtual particles. And so the more energy that is needed to be borrowed, for lack of a better word, then the shorter the time that they can exist. In the context of this video, I'm talking about a photon coming in, changing to some kind of particle with mass, and then doing some annihilation and going back to photon. But you started with some kind of photon with energy. But I'm saying that the weirdest thing of all is that even in empty space, if you go way into deep space, no mass anywhere, no energy, no photons, no nothing. It's just nothing there. Even in empty space, depending on the conditions, particle-antiparticle pairs can pop in and out of existence even there. You may have heard of this. It's called virtual particles. But the only way it works is that you might say, well, that violates conservation of mass. It violates conservation of energy. But what's going on is there's a Heisenberg uncertainty relationship between energy and time, just like there is between momentum and position. You may have heard of that one, energy and time. And that basically means that if I want to borrow energy to create particles in the universe, then they can only exist for very short amounts of time before they must then decay and annihilate. And so this popping in and out of existence can happen as long as the timescales are really, really short. I know it goes against everything your common sense is telling you. That's okay. Common sense doesn't apply to quantum mechanics. I'll be totally honest with you. It's totally mind-blowing to me that even in completely empty space with no photons around at all, these particle-antiparticle pairs are constantly popping into and out of existence. The bottom line is that what we think of as empty space isn't really empty at all, and you just have to recalibrate yourself to believe that to be true. It's really a bubbling, churning sea of virtual particles popping in and out of existence according to the Heisenberg uncertainty relation. Remember, it tells us that there's a fundamental uncertainty between energy and time, and the smaller time interval that we choose to look at, the less certain we have to be about the energy happening at that moment or that interval in time. And basically what this means is that if the particles appear and disappear quickly enough, they can temporarily borrow from the universe, for lack of a better word, the energy needed to exist, as long as they, quote, pay it back fast enough by annihilating each other again and disappearing fast enough so that it obeys the uncertainty relation. And the more massive the particles, the faster that they have to disappear. And this is because the more mass that you have in your particles, that equates to more energy. And because the more energy that you have, the smaller the time interval for the uncertainty relation to hold. Now, these virtual particles are actually called vacuum fluctuations. They have real effects that scientists theorize about. They're responsible for something called the Casimir effect between close metal plates, which is a real physical effect. And they're even thought to be the cause of black holes to slowly evaporate through what we call Hawking radiation. You may have heard of a famous scientist named Stephen Hawking. You may have heard of something called a black hole. Everything that falls into a black hole stays in the black hole. That's what we're always taught, right? Well, actually, there's an event horizon where anything that is just on the inside has to stay in the black hole, and everything on the outside is somewhat safe, right? At least if you can stay away from the event horizon. But if this virtual particle popping in and out of existence is always happening, and if it always involves a particle with its antiparticle appearing, then what happens if a particle-antiparticle pair actually appears in the quantum vacuum fluctuation right on top of the event horizon? So if here's an event horizon, and I have a particle-antiparticle pair pop into existence, before it can pop out of existence, maybe one of the particles gets sucked into the black hole, and the other particle is flying away from the black hole. Well, then that would mean that some mass is escaping the black hole. And it turns out that Stephen Hawking theorized this, predicted its effect, and basically said that the radiation that was escaping the event horizon would be called Hawking radiation. But if you give it long enough, the black holes will gobble up matter and then eventually begin to evaporate due to Hawking radiation. Virtual particles appearing near the event horizon, some of them fall into the black hole, some of them escape. That means matter and energy are escaping the black hole, and it eventually shrinks down and disappears from existence. But when we add real photons with a large enough energy, like in our light bouncing experiment that we're talking about, they can provide the energy needed to turn these virtual particles into real ones that stick around long enough to interact. And as we said, it can appear that the photons are bouncing off of each other, even though there's a much more complicated process happening down at that level, and they're not really bouncing off of each other. Now, scientists are actually studying these light-light interactions right now using large machines like the Large Hadron Collider at CERN. Now, by colliding extremely energetic particles, they can create conditions where photons might react in this way. And recent experiments have even managed to observe evidence of photons scattering off of other photons, something that was purely theoretical when Einstein was around. So there you have it. Light can bounce off light, sort of. Well, it really doesn't, but it can appear to us that way in our experiments, but only under the most extreme conditions and only very, very rarely. It's just another reminder that quantum mechanics is full of surprises. Richard Feynman once said at a conference with the brightest quantum mechanics minds in the world, "I can safely assume that nobody understands quantum mechanics," and I think he was correct. It seems really, really weird because it violates our common sense, and we're still uncovering new mysteries about quantum mechanics and the nature of light and matter. I'm Jason. Thank you for hanging out with me. Please do drop me a line. Let me know what you think, and always remember to stay curious. Learn anything at mathandscience.com.